My name is Johannes Demel, you already know that. I'm with the Department of Communications Engineering at the University of Bremen. And today I'm going to talk about an ultra-reliable, low-latency, over-the-air communication system in GNU Radio for automated guided vehicles. So imagine we have an industrial indoor scenario, like a factory hall. In that hall, we have automated guided vehicles. So they are robots. These are controlled by a central AGV controller. So this controller will always tell each device what to do next, send commands. All the devices will report their status. And they will do that in a closed loop fashion. Well, and then they will communicate wirelessly, because otherwise we would get in real trouble with cables. Well, the question here is, what are the actual communication system requirements in such a situation? So we were looking at ultra-reliable, low-latency communication. The ultra-reliable part for us actually implies that we look at consecutive packet errors. So if that system has an issue that one packet on a link gets lost, that's okay, can compensate for that. If the next packet gets lost, that might actually be critical, and if the third one gets lost, well, you might have to shut down the whole system, send in a person to reset it into a known state, all the while your production line comes to a halt, so that's really a bad thing. So we need to avoid burst errors. The other part is low latency. Depending on the documents you read, you will come up with, or you will encounter values like a requirement of end-to-end latency below 1 millisecond. And furthermore, a real-time deadline. So if any packet is delivered after that deadline, it will be discarded, it will be considered lost, which is actually a problem because then our reliability constraint comes into play. And furthermore, we look at periodic deterministic communication with small packets. So we usually only have like 32 bytes to 64 bytes, something in that range, that we want to transmit. And we do that in a cyclic fashion. All right, so how do we implement that system? Well, first of all, what do we want to implement? We look at a Cloud RAN scenario. Cloud, for us, implies that we have abstract compute resources. We will develop under a software paradigm. And we want to explore the platform specifics, like we want to characterize the DSP latency and how things work out for us. On the other hand, we look at a radio access network, and here we want to look at ideas like a distributed access point, or multiple of those actually. We want to do joint digital signal processing, and then also we want to verify that all the technologies we decided were a good fit actually work as expected. So the question would be, can we implement that in GNU Radio? Here we first look at what do we have, where do we want to go? The current system actually uses Wi-Fi. Well, it runs at 2.4 or 5 gigahertz in the ISM band, and it needs to do listen before talk. So currently the application has a periodicity of their updates of 100 milliseconds, and the requirement would be to lower that periodicity. But the current system is too unreliable to do that. So we want to implement our own system in GNU Radio. It's supposed to run it in the 3.8 gigahertz band. That would be the N78 band for 5G. And we have a dedicated campus network, so we actually have an exclusive license. And then the goal is to build an optimized communication system where we have a target of 20 millisecond periodicity with high reliability, with low latency, and actually good support for short packets. And then the question would be, how do we improve reliability? We look at different diversity options. First, we look at time diversity. Here, we sometimes encounter problems like shadowing or blocking, like in the picture below. You can see the mobile unit is behind the wall, and it's a blocking situation, and that will not, solve itself within our latency budget. So we will hit our deadline, and the whole system will need to shut down. So time diversity will not do it for us. Next, we're looking at frequency diversity. Here we need to know that even if you have a line of sight in an industrial scenario, typically you have Rayleigh fading. And also you usually have quite a large coherence bandwidth. Well, so frequency diversity doesn't do it for us. Thus, we look at spatial diversity. Here the idea is that we can mitigate shadowing and blocking because, you know, we have multiple distributed access points that are combined. And even if one link is really bad at the time, the other is hopefully not, or at least the likelihood is way lower. And also we have independent fading paths, so that's also really nice. You've seen Matt's presentation yesterday. We would assume we have a correlation between those paths that is around 0. Great. So spatial diversity it is. Here, specifically, we look at the idea that we have a joint decoding in the uplink. So a device transmits a packet. We have multiple access points that receive it. Then we do some processing individually. For example, we do demodulation, we do demapping, and then we actually obtain LLR values that we can just sum up and feed them into a decoder for joint decoding. And then thus we improve reliability. In the downlink, we look at something called cyclic delay diversity. So from one access point, you just send the original message signal in that situation. From the other access point, you send a cyclically shifted version. Works very well for multi-carrier systems. For, in this example, GNU. And what you actually do is you introduce artificial frequency selectivity, and you can just compensate that in your receiver with your equalizer, and you have two different paths now, and you don't run into situations where you have to worry about destructive interference just because of phase differences if you would just transmit the same signal on different antennas and access points. So our approach is to have distributed access points and joint processing. All right, so let's look at our demo implementation. Well, our application actually uses Ethernet, and we just create another Linux Ethernet interface. Then we use foo over UDP. Then we have a socket PDU block in our GNU Radio flow graph, which just accepts these UDP packets. So actually, it's pretty easy to integrate that into our GNU Radio system. Then we have our DSP. That's all in GNU Radio. Everything's implemented in software. We use polar codes with a code rate of 0.44. We use QPSK, and we use GFDM multi-carrier modulation. And then we have our front ends. Here we focus on N310s and B210s, depending if they're, depending if it's a base station or a mobile unit. All right. So let's look at the hardware here. First, the base station. We have antennas with, they go from 3.3 to 3.8 gigahertz. We will always use a 2x2 MIMO configuration for our demo, but we can flexibly scale that. And we'll have a custom ground plane that you can see here. And these are then mounted on an antenna rack. Our access points are actually N310s. They're connected via fiber to a central, and they are synchronized with an octoclock with 10 megahertz reference and a 1 PPS. And then we will have a 30.72 megasamples per second sample rate for all of these. And our Cloud RAN platform is a 32-core Ryzen 3970X with 64 gigabyte of RAM. On the mobile part, we have our mobile communication hardware. First, again, we have the same kind of antennas with a custom ground plane. We have, as you can see, a 2x2 MIMO configuration. Transmit and receive antennas are actually separate here. And then we have our front end, in this case, a B210, that's connected via USB to our computer. And again, we use the same sample rate, the 30.72 megasamples per second. And then we have a computer on that thing, 12-core Ryzen 5900X with 32 gigabytes of RAM. And then we can just switch out that Wi-Fi gateway I mentioned earlier and connect our system to the internal Ethernet on our AGV and just replace the communication system. I think that's really neat that we can just do that. And, well, we have another battery in there to always be sure that we have enough juice. All right, why do we actually use GNU Radio? Well, first off, I have this great quote here. It's like two drunkards trying to share a beer. Sooner or later, they're going to get into a fight. So what we actually want is someone to organize that bar fight for us. We don't want to do that ourselves. And the GNU Radio thread per block scheduler does that, so that's great. Furthermore, we have a lot of infrastructure. So we have the Qt GUI, we have hardware blocks like for the USRP, we have networking, like the UDP blocks I mentioned earlier. So lots of things we don't have to implement ourselves and run through all the rookie mistakes you can do. And then GNU Radio has a very great community with helpful people. So thank all of you for giving feedback, for answering questions, and contributing to GNU Radio. We implemented a few things ourselves. First off, Polar codes. They're very good for short packets. That's one of the reasons why we chose them. You can find them on GitHub, and we have a very fast implementation there. Actually faster than the one that's in GNU Radio, because we learned things since then, and now we have a better one. All right, then we use GFDM multi-carrier. Here we have two parts. We have GRGFDM. It's actually started by Andre Rode, and we took it over, improved it, and evolved it. And then we have also a packet or an out-of-tree module that's called XFDM sync that you can see down here. It's based on Schmidt and Cox synchronization, but it does also use a cross-correlation in the end to improve the timing accuracy. And it has a very high throughput. Then we have a module for standardized symbol mapping. Unfortunately, the constellations defined in GNU Radio entry are rotated with respect to the ones you usually use in LTE or GNU Radio or Wi-Fi. So we have our own box here, and it does contain a block interleaver that is actually upstreamed at this point, and the latest 3.10 release includes it as well. All right, and then we have a support module that is intended to measure flow graph latencies. That's actually something that goes back to an idea Bastian Blessel presented a few years back. So that's something else we have. All right, just quickly, demo parameters. We will use a carrier frequency of 3.75 gigahertz. As I mentioned, that's a campus network, so it's exclusive for us. We use a sample rate of 30.72 megasamples. We want to use that sampling rate on the mobile unit and the base station for the sake of simplicity, and also B210 basically supports only that sample rate in a 2x2 MIMO configuration. We will have an active bandwidth of 29.28 megahertz. So that's actually something we wanted to do. We wanted to go beyond what LTE typically does. And then we will use fixed size packets with a 56-byte UDP payload. Then we have an 8-byte UDP header. We will have an IP header, and we have our custom header, and then we end up at a 99-byte frame. Still, we consider that to be small packets. In the end, we will have an over-the-air duration for each of our packets of around 37 microseconds. And that gives us quite a bit of spare resources to do time division multiplexing, to support an uplink and a downlink. So that's where we are. The first thing we do now is we take latency measurements, more specifically round trip time. So we just do a ping. And then we have two CPUs, two generations, the 3970X and the 5900X. And we have two different USRPs. It's important for the two different USRPs to know that we use time commands to transmit at the specific time in the future. And if you use a B210, you actually have to use a time further into the future to make sure you don't receive all those late packet errors and then don't transmit at all. So these are the values that we use, and that work quite well for us. So as you can see, our render times are depending also on the cycle time. So we only allow to transmit every cycle. And then you can see that we end up at around 2.5 milliseconds. Actually, the 5900X is a bit faster than the other. But then again, if we use an N310, our latencies will be lower overall. And you can see there's this one thing that basically says that 0 microseconds cycle time. That's when we just deactivate all the transmit at a specific time in the future thing, and then we can actually support a 2 millisecond round trip time that would translate roughly to a below 1 millisecond end-to-end latency. Anyways, our application requirement of 20 millisecond periodicity is supported. All right. Next, we wanted to know about DSP latency measurements. And here we look at GNU Radio flow graphs first. So again, we use pings to measure that. And you can see the echo part that's below around 82 to 107 microseconds. That's the part where an echo request leaves our system and until the echo reply comes back in. Then we have our TX chain that varies between 135 to 166 microseconds in the GNU Radio flow graph when we run it over the air. And we have our RX chain. So unsurprisingly, it does exhibit a higher latency that's in the area around 439 to 565 microseconds. However, how much of that is actually caused by our algorithms and how much is, well, let's say, overhead. Here we'll look at just the DSP functions that we use and measure these. You can actually see that the black bar is our specific configuration that we use for our demo. And you can see that the transmit latency for all our blocks is, well, only 9.3 microseconds. So it's an order of magnitude lower than what we see in our GNU Radio flow graph. On the RX side, it's a bit more nuanced because the faucet configuration has a latency of around 13 microseconds, and the slowest exhibits a latency of 104 microseconds. Still, it's way lower than what we see in our GNU Radio flow graph. So we actually conclude that we see a huge multi-threading overhead here. And I'm actually really excited about GNU Radio 4.0, and if the more modular and flexible scheduler will actually help us to improve in that respect. All right. One more thing, I wanted to show you some SNR measurements. First, you can see here, that's the demo area. In the middle, there's a stairwell, so it basically separates the upper and the lower part. And you can see that there are two access points. One is on the top, and one is more to the east in the middle. So we actually have this distributed access point set up. All right, and then we end up with these SNR measurements, and you can see the access point on the top is well suited to provide good SNR in the upper part of our demo area, but it falls short in the lower part. We can basically see that how the part behind the stairwell will have significantly lower SNR. And then the other access point exhibits a picture that's basically reversed. And by combining those two, we can actually improve reliability. That's something we really wanted to show, and I think SNR measurements are a good surrogate to actually imply that we improve reliability here. All right. Next, I wanted to show you a video. Here you can see one of our AGVs driving down the hall. I hope you can see that, where when it comes here down. And then you can see that we have a QPSK modulation. We can see the actual channel estimates over frequency. You can see the synchronization and how different packets are detected. And on the lower right, actually, you can see how the AGV controller or the server actually tracks the device and where it is at the moment. And then in the upper right, you can see how our database updates after a while with new SNR measurements and can plot these. All right. Let's go to our conclusion. And just to quickly recap that, we have an AGV system with periodic deterministic communication. We were talking about ultra-reliable low latency requirements. We introduced an industrial radio environment, presented our latency and SNR measurements. And then, as a result, we have a GNU Radio implementation available that fulfills our application requirements with high reliability and low latency. And as a conclusion, I'd like to say GNU Radio can support highly reliable and low latency communication. Thank you.
All right. Excellent talk, thank you. Questions?
Thanks for the cool talk. You do GFDM?
Yes.
What's the specific, like, is there a latency reason for that, or?
Well, you can argue that for GFDM, you have a whole frame with multiple time slots.
Yeah.
And you can eliminate all the cyclic prefixes except one in comparison to OFDM. So it's actually shorter over the air, only by a certain number of cyclic prefixes, but still. And also, it has a nicer spectral mask. So if your spectrum is actually really crowded, it might be useful to have a better spectral mask and, yeah, not disturb your other systems or your neighbors. One thing I forgot, quick commercial break, you're hiring, so if you're interested, there's a QR code. There's more information on our website.
So I apologize if I missed this during the presentation, but how do you measure the position of the robots while they're moving around? Is there a sensor? Do you have encoders on the, like, how's that work?
The audio is really difficult for me.
So how do you measure the position of the robots to plot them on the server overlay that you showed on the map?
How do I plot that? Well, the server and the devices actually communicate, and the devices report their actual position all the time. And if you didn't just combine all of that in a database, and well, in this case, it's an Elasticsearch database and Kibana on top. Yeah, that's how it works.